Hi, can you hear me? Perfect. Okay.
So I guess. All right. So our next speaker is Clemens, and he will be talking about Satisfiability Modulo custom theories in Z3.
Thanks. So I'm going to present here an approach of having custom theories in the SMT solver called Z3. This is a joint work with Nikolaj Bjørner sitting over there and Laura Kovács. Before that, a short introduction. So I guess most of you know SMT solvers. So SMT solvers are nice, cute solvers that support reasoning in fragments of first-order logic, which make them particularly interesting for program or software verification because, yeah, they have inbuilt abilities in reasoning for integer arrays, bit vectors, and so on. And yeah, these kind of thoughts usually occur in programs. For example, if we want to verify that the program here is correct, we can just translate it to an SMT formula. We can see here in the middle, and then we can ask SMT solver like Z3 whether this is satisfiable or not. And in this particular case, we get a model, which means it is not correct, there is a bug, and we can more or less extract from the model the assertion violation, which in this case is an overflow from I1 plus I2. However, this this hardly depends on the solver's ability of reasoning in the desired theory. For example, in this case, the solver needs to be aware what the greater sign and the store and select function means. But now, the problem we were encountering is what happens if we need some very, very specific theory that's not supported by the Z3 solver. Yeah, of course, Z3 cannot support all possible theories. That's not possible. First order logic is not decidable. And there are several ways of dealing with the problem, and I think the most obvious one is just by axiomatizing the theory we want to use manually. So some SMT solvers like Z3 or CVC5 support quantification. So if we assume that Z3 would not support arrays, we can just add the 3 array axioms, and in theory, Z3 would be able to even reason in the array fragment without having it built in. However, we would easily run then in performance problems. First, because we introduce quantifiers which are undecidable. And secondly, even if we manually axiomatize it, we won't run into memory problems. So this is probably not an optimal solution. Another potential solution would be to reduce the problem to a supported theory. So most solvers support integer reasoning. So, well, why not reduce the array problem to an integer reasoning problem? Maybe this works. There are some other difficulties, but even if we make it work, we reduced a rather easy problem, namely array reasoning, to a hard problem, namely integer reasoning. Also not optimal. So third try, we could also change the solver source code. Yeah, that will definitely work. However, it's tedious. We probably introduce further bugs. It's hard to debug and potentially not worth the effort. So what we propose is the so-called user-propagation. And I've summarized here some potential use cases for the user-propagator we dealt with. They are all related to extending expressibilities in Z3 or increasing performance. However, there are not only topics related to increasing performance, but also some others, like we could also use the user-propagator for educating SMT solving or for just as a nice framework for drafting new decision procedures. I will later come back to some of these use cases. Okay, my mouse is not working anymore. Let's try it this way. Okay, that works. Yeah, so the red highlighted ones here I'll discuss later. For the first one, this posted, you can find a summary in the Z3 documentation, and Nikolaj mentioned the aggregate case in the tutorial first in the morning. So, but first, what is actually the user-propagator? I will present this in a Q&A fashion. So, how does it work? First, we will build an arbitrary SMT formula by the Z3 API. For example, this nice formula here. And then we might say, oh yeah, I'm interested in the string constant S1 here, or in the subterm Z plus 3, which is a bit vector expression, or in this atom C minus 5 is D, or also in this subformula for all x, P of x. We can more or less register everything that is ground. However, we are not able to register something that is not ground, like this P of x here, or something that's syntactically incorrect, like this formula here. This up, whatever. And so internally, this does not. This is very easily explained. Just means introducing an auxiliary variable, respectively an e node, where Z3 is enforced to assign it if it's a Boolean or bit vector variable, and it's not allowed to remove it by simplification. Then we attach some callbacks, which are just functions that can be written in any supported programming language like C++ or Python to the user propagator. And then we ask Z3 to check the satisfiability of the formula. And whenever Z3 encounters registered expression, it triggers the respective callback. And the callbacks are allowed to then communicate back something to Z3 and this way model the desired theory. So there are three ways how the callbacks can communicate with Z3. The first is by propagating new lemmas. So assume the user propagator already knows a subset of equalities that are reported by the user propagator to Z3, and also some assignments. I'll come later back to where the user propagator can know from that these equalities and assignments have been made already. And then we just say our theory we want to model, so this is this T here, in combination with the equalities and the fixed assignments, then propagate respectively have as a consequence this arbitrary formula G here. For example, if we want to model some kind of transitivity, we can say, oh, A is equal to D. We already know this from the user propagator. We also know that this A is smaller or equal than B, or A is smaller or equal than C is true, that B is smaller or equal than D, C is smaller or equal than D, and therefore we propagate now A is equal to B or A is equal to C. So we can propagate more or less any arbitrary formula. Another way of communicating with the solver is by adding a conflict, which can be seen just as a shorthand of propagating false here. Again, an example, if we know that A plus B is assigned to the bit vector 6 by the core solver, and we know that the uninterpreted predicate is prime of A plus B is true, we can add a conflict. Both these functions have in common that E and F are used as justifications in case of a conflict, because in SMT solving, we always have to justify anything we, or more or less everything we do. A third way of communicating with the solver is by helping the solver to do good decisions for splitting. So in case the solver cannot propagate anything anymore, it can ask the user propagator, hey, my internal heuristic would now suggest, for example, setting the Boolean variable B3 to true. And the user propagator may say, no, that I would prefer if you set B2 to false, for example. But the most interesting part in the user propagator is, of course, the callbacks we can attach. And here we have this fancy picture Nikolaj presented in the morning at the Popper Tutorial Fest. The most important callback is the so-called fixed callback that is invoked every time a registered Boolean or bit vector expression is assigned to a Boolean or bit vector value. We also have the equality callback that is called whenever two registered expression for two registered expression is deduced that they are equal, so their respective representatives of the equivalence class are reported. We have the created callback, which is called whenever a new instance of a function symbol is created. So, for example, if you have f of x and x is a universally quantified variable, we get a callback if f of a is instantiated. So this allows us to reason in presence of quantification. And the last important callback I'd like to discuss is the final callback, which is called whenever the Z3 core assigned all Boolean and bit vector variables, and the final callback more or less asks the user propagator to do a final pass whether the Boolean assignments are consistent. Usually we do this to postpone the hard and more expensive checks to the very end. So now the picture is away. Okay. And there are some other callbacks I don't discuss because they are not that interesting. By the way, here's the other picture. So Nikolaj added a Twitter survey, which is the nicer diagram. So please, I would strongly suggest to vote for this. If you have time, please do that. Right now, there is preference for that one, but I don't like it personally. So please vote for it. Okay, let's come to some use cases. Where you can see the benefits of the user propagator. And I'll start with a very simple CSP problem. So consider the n-queens problem, which more or less asks to place n-queens on an n times n chessboard such that they are mutually non-attacking. So for example, this here would be a solution to the 6 times 6 n-queens problem. And there are different formalizations of the problem. So I personally like this bit vector encoding, which more or less says for the queen in the row I and the queen in the row J, they are not allowed to be in the same column. The same for the diagonal, and every queen has, of course, to be on the board. Also very prominent is the propositional encoding of the n-queens problem. I won't discuss because I don't think it's very illustrative. And there are also other encodings which are completely irrelevant for our purpose here. But let's start by looking at the bit vector encoding, which is quite easy to read and to understand. However, we have here some arithmetic expressions for example, the subtraction from Qi and Qj, which is unfortunately not that good for reasoning, because the solver now bit blasts this subtraction, although we just wanted to say that the should not be in the same diagonal. So we got more than we actually needed, and so we would need some variant of lazy bit blasting. We just want this subtraction to represent that they should not be in the same column, and the actual result of the subtraction is more or less irrelevant for us. So we can easily code this by this nice pseudocode where the respective C++ code is also not that much longer. And this more or less says, yeah, if some arbitrary queen variable here is not on the board, well, then report a conflict that this particular variable is not assigned in a good way. Or if that's fine, then we compare it against all other queen variables that are fixed so far. So for example, consider these two. If we now fix this queen variable, then we check, is it in the same column like this one? Oh, yes, it is. Okay, these two here are conflicting. And this way, we lazily build this bit vector formula. And if you just look at the code, these 3 conflict lines here correspond directly with these 3 assertions here. But this, as we will see then later, is far more efficient than what we than encoding it eagerly. Also, user propagation allows us to define custom heuristics. For example, in the CSP or in the n-queens problem, it's a good idea just to put the next queen always on the tile where it can attack most other currently not attacked tiles. So in this case, this is a good place to put the next queen on. And of course, Z3 would not be able to deduce by itself or by some general heuristic that this is a good choice for the next split. However, with the user propagator, we can easily encode to put the next queen here. Another application of the user propagator in combination with CSP is encoding AllSat very efficiently. So usually if we have AllSat problems, so enumerating all solutions to a given problem, we would usually do it by some very generic loop that just asks, is the formula satisfiable? Okay, it is satisfiable, then get a model. Okay, we want to block this model, so this particular model is not fine. And then we will repeat this until the formula gets unsatisfiable. However, we can do far better by using the user propagator. We just use the final callback. So whenever the user propagator gets reported that all Boolean variables are assigned, we just tell the solver, no, that's not fine. All variables are conflicting, and we then increment the counter. This is more efficient as we never exit the real reasoning part. So we just stick in our loop. And furthermore, the conflicts we learn this way are far more lightweight than the hard assertions on the left-hand side. So the solver core can garbage collect these new conflicts easily if they get redundant at some point. So whenever all are assigned, we just add a conflict and get another solution. Without looking at these statistics too much, I just want to point out that this vastly increased performance, both for all such problems as well as for considering a single problem. Very interesting is especially the last line. With the user propagator for finding a single solution to the 60 queens problem, in the propositional case, it only takes 60 milliseconds and 19 megabytes of memory, whereas the propositional encoding without the user propagator needs more or less 2 seconds and 128 megabytes. So it really increases performance a lot. Another use case of user propagation is quantifier instantiation. Let's consider the so-called problem for finding a minimal sorting network. A sorting network is more or less nothing but a wiring such that for all input variables in 1 to n5 in this case here, if we compare and swap them, if the respective wires are not well ordered, so for example, if this line here contains a higher value than this one here, then they are swapped. And we can then represent this as a first order, respectively a bit vector formula that says we have a wiring given by W1 to Wm. And for all inputs in 1 to in n and out 1 to out n, if we do the conditional swaps given by the wiring, then they are then the output is finally then sorted at the end. So how would Z3 deal with this formula if we pass it to Z3 naively? It will first guess the wiring given by the WIs. Then it will finish the query, do a model extraction by MBQI, then insert the found model and check the negated quantified part, so this part here. Either it is unsatisfiable, which witnesses that that this is indeed a correct sorting network, or in case it's satisfiable, this witnesses that the sorting network is not correct, and we would instantiate by the counterexample and do a soft restart and proceed by finding another wiring. However, with the user propagator, we can do better. First, again, we find a wiring that stays the same, but then instead of finishing the query and doing a model extraction, because all of these things here are bit vectors, we just check random 10 inputs for our find wiring. And experiments showed that in roughly 90% of all cases, this will already detect a violation. So we did not do any subquery, everything is fine. In 90% of the cases, we will find the violation already in this step. And this step is, of course, very cheap because it's just 10 random inputs through a wiring. And then we also don't have to insert the model. But if these random instances do not report a violation, we don't know whether the sorting network is correct or whether there is some harder to find violation. So in this case, we then spawn a new Z3 solver and check the satisfiability of the formula. And then if it's unsatisfiable, we indeed again found that this formula is indeed correct. We found a sorting network, everything is fine. Otherwise, if there is a counterexample, we can generalize this because we have now more domain-specific knowledge. We know that this is a sorting network, so we can apply some generalizations. And also because we did never finish the sorting, we just add the conflict, add the new lemma, add the instance, and we don't need to do a soft restart because we never finished. So everything is fine. And again, this vastly increases performance. easily by 100%. For example, for synthesizing a minimal 7 sorting network, this only requires 44 hours instead of 150 hours. So it's slightly better, I guess. As a third use case, I'd like to briefly discuss lazy axiom instantiation, in particular in the Alive2 use case. But I will motivate this first by, again, a CSP-like example. Assuming we have 1000-bit vectors, each of them consisting of 32 bits, and we want all of them to be disjoint, we can just eagerly add this huge conjunction of disequalities, which yields about 500,000 disequalities, just to make sure that all these xi's are pairwise disjoint. However, if we just run it with a random assignment, the chance for a collision is far below 1%. Okay, so it's not optimal. So a better way of dealing with this is just adding the disequality between two variables if they are assigned to the same value, and otherwise just let the solver do whatever the solver wants to do. To generalize this a bit more, consider this variant of the problem, which wants to make sure that if we have a set of intervals, that these intervals should be pairwise disjoint. Each interval is given by a starting address and the size of the interval. We can just add this huge conjunction again, which either says the one interval is strictly before the other one or vice versa. Again, we can do a similar trick by just adding that two concrete intervals are pairwise disjoint if the solver assigns them in a way such that they are intersecting. For example, if you have an interval I1, which is given by 1 and 4, and an interval 2 that starts with 2 and then till 5, so they are obviously intersecting, we're just propagating in this case that these two intervals should be disjoint, and otherwise we just do nothing. In the Alive2 verification toolkit, this is a quite frequently used lemma that makes sure that two allocated memory blocks should not intersect. And of course, it's very practical to not encode this eagerly because, yeah, it requires a quadratic space, and the solver also should not focus on this lemma. It's usually completely irrelevant. And also it's time consuming to generate this lemma because in the worst case, there are a lot of memory allocations that should be disjoint. So yeah, it sounds nice, but it's not that easy in general because the formulas in Alive2 actually look this way. So both the variables are universally quantified, and secondly, it's not top level. So we cannot really apply this trick directly. But what we do is just we replace this part by a new uninterpreted function symbol. We use the term user function for it because it's a slight variant of an uninterpreted function. And then we observe this new user function. We call this disjoint in this case. As its arguments, we have the universally quantified variables that define the intervals. And we now have to distinguish three cases. The first one is the solver says, oh yeah, this uninterpreted predicate disjoint is assigned to true, but there are at least two intervals that are intersecting. Okay, we don't want this case, so we now propagate an over-approximation that says, if you assign this predicate to true, then these two intervals that are intersecting should not intersect. Okay, solver will backtrack, everything is fine. The other case that's in our particular case more difficult is the solver says they are not disjoint, but indeed they are. In this case, we need to propagate an under-approximation. For example, we can take the strict ordering, which is not intersecting, as a witness that they are indeed disjoint, and say if they satisfy this property, then they should also be disjoint. Again, the solver has to backtrack. And in the third case, the solver says either they are disjoint, and they are indeed disjoint, or they are not disjoint, and they are indeed not disjoint. In this case, we are fine. We don't have to do anything. So more generally, we can always apply this approach. I've now written it here down more abstractly by F. So we both need an over-approximation and an under-approximation. If we have both, and they are both kind of succinct, then we can apply this trick to lazily instantiate the axioms. In the Alive2 case, we could additionally verify 6 functions of the gzip compression library and 3 of the bzip2 compression library with the alive2 verification toolkit just by adding this lazy axiom instantiation. Although this does not really sound much, there are not so many functions that are relevant for that make use of this axiom, so it's quite a lot. Just a very brief discussion of what might follow in the future. Especially the fixed callback is very interesting because right now we just support booleans and bit vectors. So we get a callback whenever a boolean variable is fixed by the CDCL core or when there's bit vector assigned. However, what's now about integers or strings or so on and so forth? Because that's not that easy, because usually the dedicated string solver, for example, does not know the explicit value of the variables. It just builds them in a separate step after solving. So we can't really issue these fixed callbacks. However, there are some cases in which we can, and this is also slightly related to what we heard in the previous talk. For example, for ADTs, so algebraic data types, we could in principle issue these callbacks because they are based on a propositional encoding. So the solver internally splits on the recognizers of the ADTs. And fortunately, I have exactly the same example as the colleague from before. Assuming we have a list here, we can just register whether it is nil or if it is cons. And if it is cons, we just add, during reasoning, additionally the expression, is the tail here, is the next element, so is tail of x now nil, or is the tail now another const? And we might be interested in the head as well, so we can register it as well. However, there are problems with it, and it can easily lead to non-termination, and yeah, I think we have to work on this a bit more to officially support it. Because, yeah, if we do this naively, this will cause non-termination, and yeah, it's undecidable in general, so yeah, we cannot expect this to work in all cases. Just 2 further comments. There are some solvers like NRSAT and PolySAT, which is currently under development, which are based on NCSAT. So these kind of solvers internally have a model for the variables, and they could, in principle, also report a fixed callback to the user propagator. And some solvers, especially the integer solver, internally has bounds for the variables. So it might not know what the precise value for x, but it knows it's at most 3 and at least -7. So this might also give an alternative API that allows us to query potential values. So we can ask the solver, is 3 still a feasible value, or is it already out of reach? Further aspects not related to the fixed callback may be an integration of iterative deepening and assumptions, integration for pre and in processing, maybe also external splitting. So especially if we want to have a communication between several solvers. So for example, if Z3 should talk to an ASP solver, then they have to also communicate about the splitting that was done in the external solver. And I think eternal problem will be the proof generation for this custom series, which might be a bigger topic. Okay, then thanks for listening, and yeah, questions?
So let's pretend, for the sake of argument, that I'm not an expert in the internals of SMT solvers. Is this API like something I can use without shooting myself in the foot? Is there a clear specification for the API you're exposing to these users of these, bespoke theories and propagators?
It's officially released, so if you download the current version of Z3, it's already there in the API, and I don't think you will shoot in your own foot if you use it. It's kind of documented, and
Okay.
It should work.
Oh, well, it's kind of documented.
So unless you
I'm
do
just, I'm
some
just wondering
crazy
if
things
is
with
it easy to express what the invariance of your implementation needs to be for each of these callbacks?
I think so. Yeah, if you write complete bullshit, then it will output bullshit.
Yeah, well, imagine, again, for the sake of argument, that I'm a programmer that sometimes writes complete
Yeah.
bullshit. Is there some way to sanity check these things, or?
I don't. Well, it will do exactly what you write there, because you
that's
introduce arbitrary
the
code,
problem.
and if you propagate lemmas that are kind of contradictory, you will get a respective output.
But theoretically, you could check those, right? You could have a mode where those things are checked for sanity, and then you turn it off when you want to be fast.
I guess so, yeah. Well, you can add a model checker as well. So whether the found model, if there is one, then you can check it. However, if you say unsat, yeah, the problem with the proof still persists. So
Okay.
that's probably a harder topic.
Okay. Thanks.
At the start of the slide, there was a point that. Sorry. At the start of the slide, there was a point that string solvers could also be integrated, but you have the constraint that variables can only be bit vectors. Then how would variables representing strings would be communicated?
Well, we have this equality callback that can be used for all kind of variables. So if you register, for example, the S1 variable here, or S1 constant, and it's equated to S2, for example, you get a callback. You just don't get a fixed callback for it, but you get the equality callback for it. So that's usually enough to build a lot of theories.